So imagine you're trying to take a photograph of the universe, but your camera has like absolutely no exposure control.
Oh, right. So you're just letting all the light in.
Exactly. You leave the shutter open and eventually the whole picture just blows out into this pure, blinding white. And honestly, for decades, that is exactly what has happened when physicists try to calculate quantum gravity.
Because they've been using what's called the standard flat measure, which it basically treats every single energy level equally.
Right, and then the math literally explodes into infinities, which means they have to use renormalization, like this massive mathematical workaround, just to force the answers to be usable at all.
Yeah, it's pretty messy. But for today's deep dive, we're looking at two 2026 physics papers by Daniel Tupan that actually completely throw out that flat measure. Instead, they introduce this really radical framework using the Plancherel measure, which comes from celestial holography.
And, I mean, celestial holography might sound super abstract to you listening, but practically it just means observing the universe from its absolute outer boundary. But wait, how does changing our vantage point actually fix the math exploding?
Well, it changes the geometry of how we measure momentum. The Plancherel measure naturally acts like that automatic exposure control you just mentioned.
Oh, so it stops the high energies from blowing up the equation.
Precisely. Instead of letting high-energy momentum just run wild to infinity, looking from the boundary of the universe introduces a natural, exponential drop-off. High energies are mathematically suppressed before they can even become a problem.
Okay, wait, so let me get this straight. Is renormalization actually wrong, or was it just a band-aid because we were, like, using the wrong mathematical ruler to begin with?
It was absolutely just the wrong ruler. By stripping away all the external moving parts, what physicists call the kinematics, Tupan's papers actually prove that the underlying bare loop measure is unconditionally finite.
So it's geometrically bounded, right? Like at every single level or loop of the calculation, the maximum possible value is strictly capped.
Exactly. It's capped at 1/8 to the power of that loop order. It simply cannot grow to infinity no matter what.
That is wild.
Yeah.
And because it's entirely finite, the actual measurements at the lowest levels look strangely elegant. Like at one loop, the math gives us exactly 1/8.
Right, and at 2 loops, it's exactly 1/90th.
Which are perfectly rational numbers. They're closely tied to Bernoulli arithmetic, the same math we use to calculate neat, predictable sequences of probabilities. Right. But why are they so clean at first?
Well, it turns out that's purely a graph theory coincidence. At 1 and 2 loops, the structural shape of the math resembles a simple ladder, which in graph theory is called a path graph.
Right, and at these very low levels, that ladder shape perfectly overlaps with a complete graph where every possible point is connected to every other point.
Exactly, but then by 3 loops, that structural coincidence just completely shatters.
Because the ladder gets too long to be a complete graph, right? And then the clean math just vanishes.
Yeah, instead of neat fractions, you suddenly get a certified irrational 44-digit fraction.
Yeah.
I think it starts with 0.001028 and just keeps going. The magic numbers disappear entirely.
So if the baseline measure loses that clean rationality, the wild complexity of the universe has to come from somewhere else. And the papers point to the kinematic block, right?
Yes, exactly. Think of the bare measure like a blank canvas. It's mathematically finite and bounded. The kinematics are the complex brushstrokes, the moving particles and momentum that actually paint the messy picture of space-time.
And those brushstrokes are governed by what the second paper calls the temperedness theorem, which proves that when you look at a realistic physical slice of space-time, the extreme exponential growth rates of different moving particles perfectly cancel each other out.
Right, they balance perfectly. And how that cancellation happens leads to probably the biggest revelation in the papers. The math governing this kinematic block exactly mirrors the Riemann zeta function.
Oh, wow. And the Riemann hypothesis is arguably the most famous unsolved problem in mathematics, dealing with, the distribution of prime numbers.
Yes, it is. The temperedness theorem shows that the balancing act of these extreme growth rates in quantum gravity maps flawlessly onto the zeta function.
Wait, really? It places the mysterious zeros of the zeta function directly onto the celestial framework's critical line.
It literally forms a structural bridge between the physics of gravity and the geometry of prime numbers. It's incredible.
So for you listening, the ultimate takeaway here is that quantum gravity might not actually be inherently broken. We didn't need to mathematically duct tape the universe together with renormalization.
No, we just needed to look at it from the boundary of the universe, using a measure that naturally controls the exposure. Changing the lens basically resolves decades of mathematical frustration.
Which is a huge paradigm shift, and it leaves you with this to chew on. If simply swapping out our mathematical measuring stick instantly fixes the infinities of quantum gravity and reveals a hidden link to the Riemann hypothesis, what other seemingly impossible physics problems are just waiting for us to completely change our perspective?